Have you ever wondered how we can possibly predict the weather? Or how engineers design the wing of a jet? Well, the secret is all about translation. It's about taking the incredibly complex language of physics and translating it into something a computer can actually solve. And today, we're going to pull back the curtain on one of the most powerful tools for doing just that, the finite volume method. So let's just zoom out for a second and ask the big question. How in the world do we take the messy, chaotic, beautiful reality all around us and build a working model of it inside a machine? I mean, that's the fundamental challenge, right? And the answer, as you're about to see, is going to change the way you look at a lot of things. To even begin to answer that, we first have to appreciate that the laws of nature are written in a very specific and, often a very difficult mathematical language. Okay, so take a look at this. It's just a simple metal bar, right? One end is held at one temperature, the other end at another. The equation you see below it, that's a partial differential equation, or PDE for short. It's the language physics uses to perfectly describe how heat flows through that bar. But here's the catch. For almost any real-world problem you can think of, these equations are just impossible to solve with a pen and paper. Seriously. So, if you can't solve the whole puzzle in one go, what do? Well, you get clever. You change the rules of the game with a really brilliant strategy called the control volume philosophy. The core idea here is just wonderfully simple. Instead of trying to figure out the temperature of the entire metal bar all at once, we just chop it up. We divide it into a bunch of tiny, manageable chunks, and each one of those little chunks is what we call a control volume. It's a classic divide and conquer approach that turns one massive, impossible problem into a whole bunch of small, totally solvable ones. And here's what makes this whole volume idea so darn powerful. You see, other methods might just calculate a value at a single, infinitely small point. But the finite volume method, it insists that fundamental physical laws, like the conservation of energy, are perfectly balanced and accounted for across the entire little volume. This is what guarantees that our final answer is not just a number, but something that's actually physically realistic and robust. So this philosophy gives us a super clear three-step recipe. First up is discretization. We slice up our problem into a grid. Second is integration. We apply our physical law to each and every one of those little pieces. And third is flux calculation. We figure out exactly how stuff, in our case heat, is flowing from one piece to the next. That's our roadmap. Let's follow it. All right, time to roll up our sleeves and get into the mechanics of this. We're going to see exactly how we build up our solution, one little brick at a time. So here's step one, discretization, in action. We've laid a grid over our bar. We define these key points, which we call nodes. For now, let's just focus on that central node, P. It has neighbors, which we'll simply call W for west and E for east. See that shaded box around P? That's our control volume. That's our little patch of the universe that we're going to solve first. Now for step two. Don't let the word integration scare you. This bit of calculus is the magic trick. All we're doing is taking that original, super complicated PDE and applying it over our entire control volume. This completely shifts our focus. We're no longer thinking about an infinitely small point, we're thinking about the whole volume. And what that does is it transforms that hairy equation into a much, much simpler statement, a balance sheet of what's coming in versus what's going out. And you know what? All of that complicated math really just boils down to an idea so intuitive you already know it. For anything, anywhere, what comes in must equal what goes out, plus whatever's being created right there on the spot. It's just a fundamental budget, and it always has to balance. This slide shows that idea perfectly. It's called the flux balance. Now, flux is really just a fancy scientific term for the rate of flow. So this math is simply a precise way of making sure that for our little control volume, all the heat flow is perfectly accounted for. Nothing is magically appearing or disappearing. This physical guarantee is exactly what makes the whole method so reliable. Okay, so here's where we have to be a little clever. Our flux balance equation needs to know what the heat flow is right at the edges of our volume, at face E and face W. But we only actually know the temperatures at the center of our nodes, P, W, and E. So what do? We make a very smart, very reasonable assumption. We just assume the temperature changes in a straight line between the nodes. This simple linear approximation is the key that unlocks the whole problem and makes it solvable. Now, after we plug in that straight line approximation and do a little bit of algebra, we get This beautifully simple equation. And honestly, the algebra doesn't matter. It's the result that's so incredible. Just look at it. The temperature at our node P is now connected only to the temperatures of its immediate neighbors, west and east. That's it. We've created a simple, repeatable building block, a little Lego brick of physics. Okay, so we have our fundamental building block. We've got our Lego brick. Now it's time to assemble all of these bricks into one powerful, elegant structure, the matrix. And it's actually really straightforward. We just take that simple equation from the last slide and we apply it over and over and over again. For node 2, its temperature depends on nodes 1 and 3. For node 3, it depends on 2 and 4. You see? It just goes on down the line, creating this chain of interconnected equations, all linked together like dominoes. And here it is, the big payoff, the grand finale. All of those individual interconnected equations, they stack together perfectly into this single, gorgeous matrix equation, AX equals B. We've done it. We have successfully taken a complex physics problem governed by calculus and turned it into a standard linear algebra problem that computers are literally born to solve. This right here is the absolute core takeaway of this entire process. We started with the language of physics, which is calculus, and we have systematically translated it, step by step, into the native language of computers, which is linear algebra. This is the big aha moment of computational physics. Okay, that was a pretty deep dive into the math, I know. But so what? Why does any of this actually matter? Well, because this process of translation is, quite literally, what allows us to design and build the modern world. So let's just do a super quick flyby of the whole algorithm we just walked through. First, we generate a grid. Then, we integrate to make sure energy is conserved. We make a few smart approximations to make it solvable. We assemble everything into one big matrix. And finally, we just hand it over to the computer to find the solution. Simple, robust, and unbelievably powerful. The finite volume method really is this essential bridge that connects abstract theoretical physics to real-world practical engineering. Because it strictly enforces those conservation principles in every single little chunk, it gives us solutions we can actually trust for the complex flows and forces that shape our world. And believe me, this is not just some academic exercise. The finite volume method is working all around you every single day. It's used to design safer aircraft wings, to figure out how to cool the electronics in the phone in your pocket, to forecast hurricanes, and even to model blood flow to design better medical devices. Its impact is absolutely everywhere. So I'll leave you with this final thought. We just took a really complex physics problem, and we solved it by breaking it down into simple, balanced pieces. So what other complex systems out there, maybe in finance or biology or even in society, could we start to understand and maybe even solve if we just applied that same powerful idea?